Now we're going to talk about the graph. We said in previous videos that the point of this experiment was to plot the mass in kilograms against the average time squared in seconds squared, so that we could calculate the gradient and we could calculate the intercept, and from that we could calculate the spring constant, which is the thing we said we were going to calculate in the research question, and we could see whether the data is linear or whether it's directly proportional or whether it's neither of those. Now for this first one I've plotted the graph by hand. And so here are the data points for time squared with their error bar. You'll note that I haven't plotted the error bars in the horizontal direction, and that's because for this particular case the error bars were just far too small to be seen. But they are plenty big enough to be seen in the y direction, so I plotted them. Now I have here two anomalies, so values that lie well off the best fit line, and so I've circled them and ignored them. This is one of the reasons we take lots of data points. So I have my best fit line, a line that goes through all of the error bars, or error boxes if you have error bars in two directions, and is the best representation of the data. And your maximum and minimum gradient line, so the most sloped line you can draw, which goes through all of the error boxes, and the least sloped line you can draw, which goes through all of the error boxes. You could do this on Logger-Pro or something similar, and you can use that to do your maximum and minimum lines, your error boxes, and then it will tell you what the slopes and the intercept of all of these things are. So it's entirely up to you whether you do it by hand or on something like Logger-Pro. And that is the graph itself. And now we need to discuss what the graph shows. So the graph seems to show that the data is linear, i.e. it fits. The line of best fit is straight. So it's a linear relationship. The next thing we want to know is whether it's directly proportional or not. And we said it was probably going to be in the exploration section. So that's what we suspect it would be. Now then, how do we figure out if a linear graph is directly proportional? Well, it should go through the origin. Now you'll notice that the line of best fit doesn't quite go through the origin, but that the intercepts of the best fit line, the maximum gradient line and the minimum gradient line cover the origin. So the origin is somewhere in this value, in this range rather. So what I could calculate, or read off in this case, are the intercepts of the maximum and minimum gradient lines. I could use that to calculate the uncertainty in the intercept, which is half the range of the values. And then the intercept of the best fit line is minus 0.0002 seconds squared plus or minus 0.0004 seconds squared. This error bar contains the origin. So our data is commensurate with the idea that the origin, that the line of best fit line goes through the origin. If this is true and it's linear, which it is, we can say that in this case t squared and m are directly proportional. This is important because what it is you're doing is you're describing the graph. It's linear, you've shown that it's directly proportional. The other thing we need to calculate is the gradient. So we draw some nice big triangles. So there's the triangle there, all the way down to there, and that allows us to calculate the gradients of the maximum and minimum lines and the gradient of the best fit line, and therefore work out what the uncertainty on the gradient is. Now, there is something wrong on here, and that is I've quoted the gradients, but I've not quoted their units, which is silly of me. So the gradient is how much the quantity in the y-axis changes divided by how much the quantity in the x-axis changes. So that would be whatever number seconds squared and whatever number kilograms. So the unit would be seconds squared per kilogram, and so I've put all those units in there. So we have the gradient of the maximum and the minimum gradient lines, and that allows us to calculate the uncertainty on the gradient, and therefore to quote the gradient of the best fit line. So what we've done is we've done the analysis section. We processed our data correctly, and we showed that we had by doing the example calculations. We considered the impact of uncertainties, so we calculated our uncertainties, we plotted a maximum and a minimum gradient line, and we used that to help us calculate the uncertainty in the gradient and the intercept. And we interpreted the process data, i.e. we described the graph. It was linear, in this case directly proportional, and we calculated the gradient and the intercept, both of which were their uncertainties, and that will allow us to calculate the spring constant in the next section.